Good afternoon, sir.
Ah, technical issue. Uh, I had no internet at home, and so I had to come back to office. Okay, no problem. We will manage that. So, in the last class, I introduced what is causality, and we have causalities for few elements left. So, let us see how to give causalities to junctions and two ports. So, what we have done, we have given causalities. Causality is given by a stroke at the end of the bond. The stroke then receives effort information. The on-stroke then receives flow information. Accordingly, we have already given causalities for source of effort. This has to give effort information. So it's like this. Source of flow. This has to give flow information. So this end should be on-stroke. On-stroke then receives flow information. Here is the stroke. Then we are giving causalities two ways to R element. It could be like this. It could be like this. Then we are giving integral causalities to I element. This is good causality. This is derivative causality to I element, which is not good. This is integral causality for C element. It's good. Derivative causality for C element, it's not good. So that's what we have done. So now we will go to two ports. So first two port we consider is a transformer. This transformer, as you know, has a modulus, that is the scaling ratio, as well as the orientation of scaling. So I have this transformer. I make a copy of this.
वही पूरा बोल रही थी ना ऑफर आ रही है सब इतना पढ़ने में सब तेज है वही पूरा बोल रही थी हमारे भतीजा के तो भाई ऑफर ना आए ऑफर इतना ना आ पाए
Microphone on.
वही बोलती थी हमारा बेटा के सीरियस नंबर
Now node for 2, knowing flow 1, which is given to us. If we know flow 1, what we can do is we can use the relation, scaling factor, we can find F2. That is multiplying factor times F1. So F2 is output, which is input. So if F2 is output, then we have to show this as this, so that F2 is output. So in bond number 2, we have to show F2 like this. So as a consequence, if we start with this, we'll end up with this. F2 will be output. If F2 is output, then E2 becomes input. It will become input. So E2 will come like this, which is given by this causal stroke. So our descent will become like this. So when E2 put this one, consequence will be other side like this. Likewise, in the other one, let's put the starting choice like this. Okay. So let the starting choice be like this. Then we have E1 going in. Doing E1, we find E2. How much it is? The scaling direction is always opposite. So if F1 is like this, arrow is like this, then F2 is mu times F1 and E1 is mu times E2. But now we are calculating E2. So this one will be E1 divided by mu. So that's what we find. So this is output. So E2 is output. That means we get this. Once we do that, then F2 is input, because by that causality, if E2 is output, F2 must come like this. So from F2, we find F1 is F2 divided by mu. So F1 will come. So this one comes like this. Okay? So the same transformer, we have two forms of causality. For the transformer, causalities of transformers are given as PF causality, wedge, that is PF is this, or PF is this. These two are right. If you put TF like this or TF both away, this is wrong. Such a thing doesn't exist. Right? Yes, any questions there?
Yes, sir. In the first
Yes.
case, when we consider E2 as input,
E2 as input. Yes, E2 is input.
E2 is input for E1, right?
E2 is using E2, we can compute E1. Yes, E2
So
is
E2
input.
is input for E1.
E2 is input to transformer. Okay.
Okay.
Yeah,
And E1 is output.
E1 is output, because once you make flow input, the opposite factor will always become output, because both information cannot go in same way. Okay.
Yes.
So one input means other becomes output.
Yes.
So transformers will always have this causality. Either one side clock is near, other side is away. Both cannot be near, both cannot be away. That's what is the transformer causality rule. Likewise, we go to gyrator. Note that according to causality, this equation is changing. All right. So in one equation, the transformer modulus appears as a multiplier. In other equation, this transformer modulus appears as a fraction denominator. So you understand that in the second case, if this transformer modulus somehow or other becomes 0, then we will have a singularity. So gyrator has default relation, some default relation. If you it doesn't have any modulus direction, just a modulus. E1 F1, E2 F2. Without causality, we know. Without causality, we know E1 is mu times F2. They are cross. E1 is mu times F2. E2 is mu times F1. Now this relation will again come for some causal forms. So if F1 and F2 are inputs, then we will get this as outputs. E1 and E2 as outputs.
Sir,
Yes.
sir, can you once show the bond graph for the second transformer?
Graph for the second transformer.
Second part, like you have described two parts, right?
This one?
Yes, sir. Sir, so normally the transformer modulus is written for flow, right? Like If we
Yes,
put the
yes, yes.
arrow towards the right direction, then
It is always for the flow.
so then F1 will be equal to mu F2.
But no. That arrow is arrow direction. You look at that above. Above mu, there is a orientation.
Yes, sir.
That defines how the flows are scaled.
Yes, sir. So what does it mean? Like F1 equal to mu F2? That
No,
arrow
no,
towards the right means?
no. That arrow above, the arrow here, this arrow. This arrow
Uh,
says F2 is mu F1.
uh,
Okay,
oh,
F2 is mu F1 by default, but now we want F1 as output. Right, so we have to invert the flow.
okay.
So this generator, let's put again two forms of causality. Generator, generator. In one case, let's give it flow. I put that stroke. This. So I have given here flow. What I have given? Flow 1 input. Using flow 1, what can we calculate? Flow 1 is known. So we can calculate E2. So if 1 is known, if 1 is input, then E2 is output. E2 is equal to mu F1. So E2 is output means stroke should be here. E2. That's it. Okay. So that is the normal relation. If F1 is input, E2 will be output. And consequently, E F2 becomes input and E1 is out. E1 is equal to mu F2. So that comes exactly opposite direction. E1 output. Here, of course, F2 is input. So that is what is normal form. In the second form, let's give the opposite. Here, let's give here. So if that is the case, E1 is input. If E1 is input, we find F2 is equal to E1 by mu. So F2 is output. F2 will be output. So stroke will be here. F2 is output. Right. Consequently, we will have E2 is input and F1 is equal to E2 by mu is out. So E2 becomes input, F1 becomes out. So these two forms are possible. So if you look at this, these two forms are exactly the same forms which transformer did not allow. Transformer cannot have these forms. Transformer has one near, one near, one away. Here one near, one away. Whereas the gyrator has both near or both away. So here, even number of strokes, other strokes are near gyrator. There it is only one. One stroke near transformer. In gyrator, either 0 or 2 strokes near transformer. That's what is the rule. Of course, for gyrator, anything like transformer, this or this are wrong. They are wrong. Both of these are wrong. Okay? This is correct. This is correct. But in one case, we will get reciprocal of the modulus. Let me put the modulus in both of them. Okay, so this is simple rule, very simple rule for generator. So transformer and generators are done. Right. Now we have only junctions. Let's say we start with one junction with some bonds. Let's say this. So we have a junction, one junction like this. What we know for this is those are same. F1 is equal to F2 equal to F3 equal to F4. That's fine. What else we know? We know for this E1 F1 minus E2 F2 minus E3 F3 plus E4 F4 equal to 0. So you have E1 minus E2 minus E3 plus E4 is equal to 0. This is acausal. This is acausal relation. Means without causality. So in causal form, we choose one as output and rest as inputs. Any one of them we can choose as output. So in this case, arbitrarily, let E2 be out. Then what do we have? E2 equal to E1 minus E3 plus E4. So that's the relation we will have. How do we put that in picture? In picture, put this by causal strokes. So what do we have? E2 is input. Okay? So I will redraw that picture. So in this, we have chosen E2 as input. So E2 will be given to the system. E2 will be given to the one junction. And what else will happen? E2 is given to one junction stroke then. Sorry, E2 is output. E2 is output. E2 will be given by one junction. And E1, E4, E3, which whatever their plus minus signs, they will be given to one junction. Okay? So this is the picture. And here, right, so according to this, E1, E3, E4, right, these three are causes. E2 is effect. So this is what we have put here. Then bond 2 is called the strong bond. Of one junction. It is called strong bond. Why strong? Because this is the one which gives flow information to the system. I redraw again that. It's 2, bond number 2, 1, 4, and we have given our causal strokes as indicated. So there are 4 bonds. 4 bonds. And flows are equal. So who decides that flow? We have a question related to parity here. If you get, let's say, some feedback from 2 or 3 different places, there is no guarantee that it will be same. For example, how many COVID patients are there in Kharagpur? You ask 10 people, you will get 10 types of answers. Somebody will say, okay, it's too much. Okay, lot of students, lot of faculty are affected, 100 people are affected, hospital is overflowing. Someone will say, no, only 10, 20 people and it's okay, everything is working normally. Someone else will say, no. So lots of rumors can come in. So always it is important to get information from the official source or one nodal source from which you will get information. So here 4 things are equal, and if we get that information from 4 places, there is going to be confusion, there is going to be a loss of parity. That's why there should be only one bond which should decide what is the flow in this junction. And that one bond is the strong bond. As for causality, what we have done, we have said this E2 will be output. Simultaneously, this F2 becomes input. So F2 becomes input. That means our F1, F3, F4, they will become outputs. So your F1 go out, F4 will go out, F3 will go out. And all of these will be same as F2. So F2 is the master, which will tell, okay, I am the one responsible to give the information. I will provide flow to one junction. Rest, whoever are there, this is the value. You report this value to all other parts of the system.
Sir,
Yes.
In this kind of bond graph, how would we handle cyclic graphs? Like, let's say to the right side of bond 2 and to the right side of bond 3, there are some other elements which in turn form a cycle. Are we saying it's impractical to have cyclic causality, or
No, it's possible.
can we have cases?
You can have cases. You can have cases. Okay. You can have cases. But unfortunately, previously I used to cover those. Okay. Something called causal loops. I don't know. This time maybe we will be falling short of classes. There are some things called causal loops. Some causal loops you can eliminate. Some causal loops you cannot. You cannot means the same thing repeats itself on itself. Okay. It can happen, and that can indicate some kind of a hidden constraint, and it may not also indicate hidden constraint.
Okay. When there is a redundant element in the system, maybe we can have causal loops, right?
Not really redundant element. Not really redundant element. If time permits, I will give you some example. Okay. Algebraic loops we can get. no problem. Algebraic loops again are cycles, we can solve them. So, what is an algebraic loop? Is simple like this. If you have a block diagram, let's say some block diagram like this, let's say plus, here minus, and here you have some kind of relation which doesn't have integration. Let's say I put 10, the value. Okay, this is x. This is my output. Y. I take here, let's say I put again I put it back. This is an algebraic loop. Okay, there is a cyclic closure. What it says is this element, something, let's say intermediate element is E. So E is equal, Y is equal to 10E. You have, then again, E is equal to X minus Y. So you will eliminate from this E and directly write Y in terms of X. Okay, so you put that, so Y becomes 10X minus 20Y. So you have 21Y is equal to 10X. So Y becomes, Y is 10E. E is equal to X minus 2Y, correct? E is equal to X minus 2Y. So Y is 10 times E, 10 times X minus 20Y. Okay, fine. Okay, so 10x, Y becomes 10x. So 21Y, yes, fine. So 10 by 21 x, 10 by 21x. So all this thing is basically x with again 10 by 21 y. But unnecessarily we have modeled it like this. So that's a redundant loop which has no value. We can remove that. So that's an algebraic loop. But a causal loop is very serious, where x will somehow or other, okay, again depend on itself in such a complex function form that you cannot separate that. Okay, so we have this. So here, what we will have relation F1 is equal to F2, F3 equal to F2, F4 equal to F2. F2 is flow, is strong bond. So that's the bond which decides the flow at the structure. Flow at this junction, sorry. And so these are the strong laws of junction. These are strong law. And we have from weak law, we have causal relation now. E2 is equal to, now we have written it previously. E2 is equal to E1 minus E3 plus E4. Plus E4. So what you see, E1, E2, E4 input, E2 output. Okay. Okay. So E1, E2, E4 are inputs, E2 is output. Conversely, F2 is input. So if E2 was output, F2 is input, the pair. And corresponding to this E1, E2, E4, F1, F2, F4 are outputs. Okay. Here, in this relation, inputs and outputs, depend on causality. The plus minus signs depend on power direction. So inputs and outputs, that means LHS and RHS, these are depending on causality. The plus minus signs and the relation, they depend on power direction. Power direction and causality are completely two different concepts. Right? That has to be very clear. Power direction has nothing to do with causality. So what we get? Rule for one junction. So at one junction, one bond brings flow formation to the junction. That bond called strong bond has causality away from one junction. All other bonds called weak bonds have causality near one junction. So you have one junction, let there be hundreds of bonds, doesn't matter. Only one will be away, rest others are near one junction. Okay? So this is the strong bond. These are all weak bonds. That is the causality rule. Simple rule for one junction. Whatever all these things are weak bonds, right? And that one is the strong bond. This one is the strong bond. That is the rule. So I have discussed this about one junction in details. For zero junctions, it's the dual, so-called dual formulation. Whatever happens to one junction, the exact opposite happens to the zero junction. Exact opposite happens to the zero junction. Whatever happens to the transformer, exact opposite happens to the gyrator. So in system terms, those are called dual formulation. So causality at zero junction, one strong bond, as usual, it brings effort, information. Because efforts are equal here. That's it. That's the rule. Okay. One strong bond, it brings effort information. All others, other weak bonds, they are and transfer that information. Whatever information this comes, they just transfer it. So as we did for one junction, one bond brings flow information, At zero junction also, one bond must bring effort information. So we have zero junction. I put some arbitrary things. Let's call E1, F1, F2, F3, 4, F4. One of the bonds brings effort information. Let that be something. Let that be E4. Let bond 4 be strong bond. So this gives effort information means that will be having causality near the junction. This is it. So that E4, if it comes, all others must take away that information, keep that information outside. So whatever E4 comes, all others transfer that. That's it. And consequently, so E4 is input. So what we have, F4 is out. So this is strong bond 4. That means E4 is input. Consequently, F4 is out. So we can write these relations. What we have, strong bond is 4. So E1 will be E4, 2 will be E4, 3 will be E4. Whatever n number of things are there, those will be E4. So here, this is strong law of zero junction, and same zero junction has weak law. So as for weak law, we have F2 input, F1 input, so on, F3 input, F4 will be out. So F4, this side E4 has appeared, means F4 will appear on the LHS. These E1, E2, E3 has appeared in the LHS, implies F1, F2 and F3 will appear on the RHS. So F4, F1, F2, F3. As per causality, they are on RHS. Now plus minus sign. So by looking at this picture, we should be able to tell which one is plus, which one is minus. I say F1 is plus, F3 is also plus, F2 is minus. I directly say this. How do I say that? Directly. Look at this. We have E1 F1 in minus E2 F2 power minus E4 F4 plus E3 F3 equal to 0. This is our power graph. Efforts are same. So you have F1 minus F2 minus F4 plus F3 is equal to 0. We have taken F4 that side, so we got F1 minus F2 minus F3 equal to 0. But I wrote it directly without even writing this. What did I do? I checked. If this power direction, if it goes through this like this straightforward without reversal. So F1, this bond with whatever power direction goes through this and comes here. No problem. So that will be plus. Likewise, this E3, F3, this is into the junction. If this is into the junction and the one which we are writing equation is out of the junction, then that in power direction goes to out power direction with plus sign. This is in power direction goes to out power direction with plus sign. But this is out power direction, this is again out power direction. Right? So that will appear in minus sign. So that's a straightforward rule. Something with in power direction will go to this one, out power direction. because of the difference in power direction with respect to the junction, it will go as plus. You look with respect to the junction whether it is in or out. So in going to out is plus, whereas out going to out, there will be minus. Likewise, in going to in will be minus, whereas in going to out or out going to in will be plus. So that is how you can directly write this equation. So we have got all those rules. The total set of rules. Are what we require basically. If this, if this, are these, no problem. I am not writing the differential causality one, that we are going to avoid. I see transformer, generator, and we have for sensors, we have already shown what is for sensors. This is for PVF. That we did in the last class. Okay. These sensors, this detector of flow must get flow information. This detector of effort must get effort information for the system because it has to measure effort. So it must get effort information. This has to measure flow. This must get flow information. That's nothing great about this. So these are all the rules. We will try to follow these rules. So these rules will not be followed arbitrarily. There will be some specific discretions. First of all, we can have nonlinear elements. Or constitutive relations. For example, we have something, let's say this is force, this is velocity. We have this picture. Or we have friction force, mu n, friction force times velocity. Let's say we have something like this picture. So if you look at this, you can write F is single valued function B. So given any B, you will find one value of F. But the reverse is not true. Suppose you give some F, you give some arbitrarily F. You have two values, some F. You have two values, or some F here. You have nothing, no value. Okay. So given a F, you may not get a B. So some functions may not be single valued, some function may not be invertible. Right? So we may have multi-valued functions or singularities or indeterminacy in some causal forms. And thus, there can be preferred causality or nonlinear elements. As far as linear things are concerned, everything is fine. We will go by that rule. But if it is nonlinear, for example, this is force versus velocity. What does it mean? It is resistance. It is a resistance. And what should we do for this? We should give a velocity. We should give V and get F. This is good. But if you do this, give F and get V, this is wrong. Okay? So we have, even if we know for R element there are two forms of causality possible, for linear R it's fine. For this particular nonlinear R, we would prefer to give a velocity and get a force out. So we would prefer this kind of causality for this particular element. Alright? Maybe it's opposite. So some other way, let's say it's like this. Instead of like this, let's say it is like this. It could be some function like this. Right? Then maybe we will say we will give this, not the x-axis value. So everything is possible. Depending on characteristics of that particular element, we may specify, if it is nonlinear, we may specify some preferred causality. So using these, let me write down how to assign causality. This is what we will write as sequential causality. Note the spelling of causality. Causality. I have written many people writing Ca, that U comes after S and the result is obvious. So causality and casualty are not same things. Many people say casualty. Okay. So sequential causality assignment procedure. Or in short, SCAP. This is an algorithm. So I am not going to draw it in a flowchart. I will just write in steps. Step 1. Assign fixed causalities to sources 1 by 1 and propagate. There is a term here, 1 by 1. I will emphasize that. 1 by 1 means you don't do it in a batch. You do choose one of them, complete that, then go to the next one. In step 2, so these are fixed causalities because sources have fixed causality. You cannot change their causality. You cannot say a source of effort will give flow. Right? That's ludicrous. So you cannot do that. So let's say step 2, we will now choose assign if you have assign preferred causalities to nonlinear elements. Of course, if any, because every model will not contain this. 1 by 1 again and propagate. Okay. So if nonlinear elements are there, we have this step. If they are not there, we don't have this step. In step 3, assign integral causalities storage elements means the ones that store energy, I and C. But we know this and this. 1 by 1 and propagate. Okay? Here, usually in mechanical systems, choose I elements first and then C elements. Because in mechanical systems, these I elements are associated with degrees of freedom, and we deal with degrees of freedom. You don't see electrical engineer talking about degrees of freedom. For them, rather, it is degrees of compliance. So for them, they are interested in distinct potentials, whereas we are generally interested in distinct velocities. So we will choose I elements first, whereas if it is an electrical circuit, we will choose C elements first. Likewise, if you are dealing with a thermal system, you will choose C elements first because inertia doesn't have much of role there in thermal system. So C elements will be chosen first in hydraulic systems, in thermal systems, in electrical systems, and so on. Whereas in mechanical systems, we will usually choose I elements first. We will give preference to I element. After completing on inertias, then we will look at what happens to the springs. So this is step 3. By this time, by this step 3, whole model, that means all bonds, are generally causal. If not, then the model has loops. So if you do not get complete causality by step 3, there are loops in your model. These loops can be of many kinds. So there are many names for these loops, something called algebraic loop, something called differential algebraic loop, something called zero order causal path, and so on. In graph theory, there are many things for these loops. So we don't care about that. We usually will not go up to that stage. We may encounter algebraic loop, but I will discuss in step 4. If we come to this step, assign arbitrary causality to R elements. These are linear elements because all nonlinear elements are already covered in step 2. So these are linear. So we can give arbitrary causality. Assign arbitrary causalities to R elements one by one and propagate. If the model gets fully causal, then there is algebraic loop. If not, then there is causal loop. And go to step 5. So model should get completely causal if you choose arbitrary causality for R elements. If that still doesn't happen, then you have big problem, that is causal loop. Here give arbitrary causality is, so all ICR are done, sources are done. What is left out? Right. Nothing is left out. Give arbitrary causalities to internal bonds. So whatever bonds are not causal, give them arbitrary causality one by one and propagate. So basically, you start with sources, propagate. If you don't have nonlinear elements, forget about step 2. Choose integral causality to I elements in step 3, propagate. If the model is not completely causal, keep integral causality to C elements, propagate. Your causality should be over. If not, choose some arbitrary causality in linear R element, propagate. By that step, whole thing will be done. In your course, you are not going to step 5. So by step 4, even excluding step 2, it should be over. So let's see how we are going to do this. I will take an example and we will do it. I will take black color. Okay. Example. So let's take, here is a mass, let's call M1. There is a spring K1. There is a damper, let's call R1. Let's put a velocity source Vt, deliver. This side distance is A, this side distance is B. Put another spring K2, mass M2, gravity acting downwards. So that's a very simple system. We might put a sensor. Let's have a velocity bell sensor. So some kind of a velocity sensor is there. If you want, you can put FT, it doesn't matter. So I create its model. You have one junction, I is to N1, source of effort is equal to FP. Oh, where is source of, no, not FT, it's not there. It's 2 minus M1G. Then you have your transformer, value is minus B by A. Orientation like this. Causality has got nothing to do with power direction, so it's not required to give power direction if you are going to give causality. Then here you have this spring, the force acting at end of the lever, force through the spring, and the spring force acting on the mass axis. So I will put a zero junction. You do step by step manner, you will get the same result. So here you have K2, then you have inertia, but we have with inertia, gravity, so I will put one junction. If gravity is not there, I will straight connect here inertia. So that's the thing. Now we have something else left out, this bottom part. Again, this one, we calculate relative velocity between this one, mass, and the velocity given. So to calculate relative velocity, we use a zero junction. This is relative velocity. This is source of flow, that is dt. Okay, so this is the relative velocity. If you call this to be x1 dot, this to be x2 dot, x2 dot, x1 dot. So you have relative velocity here, and the relative velocity is the deformation of the spring, and that is also deformation of the damper. So what we have, the force of the spring and damper combined acts on the ground, same force acts on the ground, same force acts on the mass at the top. Okay, what else we have? We have a sensor. We have sensor, the detector of flow. So that's what we have. Now we will cause this. First step, sources. So I am putting that in, let's say, some color, blue color. Sources, what we have? AC must be like this, SF must be like this. So we choose any one of them, AC. Now we see if this AC causality can be propagated by this one junction rule. What is the rule of one junction? We must have one strong bond that gives flow to the junction. But there, this is a weak bond because this gives effort, not flow. So we have another 3 bonds left. So 3 contenders to be strong bond. Who is strong, we don't know. Okay, we cannot arbitrarily give that you are strong. They have to fight it among themselves and find out who is strong. We have got no role to play there. So we will say, okay, we cannot proceed further. That is what is meant by propagation. We are not proceeding further. We take another source. Can we propagate? No, we cannot propagate. Then we go to this one. This. All 3 sources we gave, but we could not propagate. No propagation was possible because by rule of junctions we could not propagate. So what are the rules of junctions? We know these rules, propagation rules. One, this is rule. 0, 1 close, others away. This is rule. Transformer. This is rule. Director. This. These are rules. We can apply those rules and propagate. Okay. Here we are unable to propagate. So now, in step 2, I will choose integral causalities of I elements. Step 2 is not there. Not present. So no step 2. We go to step 3. We give this and propagate. Yes, somebody wants to speak. So in step 3, we give, this is a mechanical system. So we will give 2 I elements and we will propagate. What are the I elements? Choose one of the I elements. So once I put this, got some rule click in. Once I do this, my rule, this one junction rule, what does it say? One strong bond away from the junction, all others should be near. All others should be near. So once I do that, SC1 and 2 things, okay, once I do that, SC is to minus M1G, 1, I, and something, this side transformer and something, whatever is there. Once I do this, right, this here and here, we will put the remaining causal strokes. So because of this and this, by propagation. As per rule for one junction. One junction rule is one causality should be away. We already have one causality away. Rest others should be near. One of them is already near, so other 2 will do. So that's propagation. So that's a propagation. Then what else we can do? Once you do this transformer, you have this, then what we do? Next one, this is by propagation. By propagation. So we will go to that transformer and put that. Right. So I will propagate this I am putting here. Once that I comes, this and this. Once this comes, this is by transformer rule, propagate. What else? Any further propagation possible here? No, this is not strong bond of zero junction. Zero junction can have one near, all others away. Here we have one away. So out of these 2, anyone can be near. We leave it. We cannot propagate. Look at this zero junction. Look at this zero junction carefully. What has happened? 2 bonds are caused away from zero junction. There are total 3 bonds. two bonds are causal away. That means this bond is not giving effort to junction, effort is going from zero junction. This bond also, effort is going from zero junction. This is giving flow. So there is no strong bond right now at this zero junction. And only one bond is left. Only one bond is left. So already two are weak bonds for zero junction. We require one element to have at least, okay, one bond to be strong bond. So we have to put this. Okay, so this is necessary because this doesn't have strong bond. This 0, 0 like this, then this must be strong bond. So we have put this. Once this is strong bond, then what has happened? One junction causality, only one can be away. This one junction, one is away. So these two are here. Okay. So we started with just this one. We started with this one. We propagated to these two because this is strong bond of one junction. Then once we did that, we propagated it through transformer by rule of transformers. We could not go further. Then this source of flow already causality was there. So by using those two, we have to apply zero junction causality rule, which says that one bond must be causal here, all others should be away. We already have two away, bond must be near. We put it there. Then again, according to this one junction rule, if we have a strong bond like this is giving flow to one junction, then other two must be weak bonds. So this propagation is complete. Okay. So now we choose other eye. Next eye. So this is done. Then we choose next eye. If all I are finished, then we will go to C. So next eye, what is there? This one. So as per rule, we will put it integral causality. Once we do that, this is strong bond of one junction. So these two must be here by propagation. So this is by propagation, these two are here. Once you do this zero junction again, two of them are away. So one must be near. So this comes here. So that finishes the whole thing. Whole model is causal by this process. Okay. So you have to follow the steps. You didn't even touch the causality of C elements. Those two C elements K1 and K2 have automatically come in integral causality. We did not give them. They have come there in integral causality by propagation. We did not touch them. We started with sources. Then we gave to one inertia integral causality. Something happened to rest of the model. Then the other inertia we gave integral causality. Again, rest of the model got causal. And then all bonds are causal. We have got nothing left. So this model is perfectly fine, very well computable. No problem with this model.
Sir,
Yes.
sir, in this, like, if, instead of giving preference to I, if we would have started with C elements, would we arrive at the same model, or would it be different?
Yes, same thing. Same thing. If there is no differential causality, you will get same thing. No problem. But in mechanical systems, we usually start at these because you will see by giving I, you will finish the causality quicker by propagation than giving to C's in mechanical systems because of the structure of the model. You see, if you give to this C instead of rest of the things, then you cannot propagate, nothing happens. This C, when you give, you can propagate to two sides. And then you can propagate to this side of a small propagation, but nothing else will happen. So by choosing C elements, your propagation will not proceed much. Whereas in electrical circuit, by choosing C element, you will be at an advantage. You will quickly causalize the model. So quickly, I will show another model. Model with different causality possibilities. One model, just one model. I have very simple system. Mass, there is a spring, there is a damper, followed by another damper, followed by a source of flow. It can have some force, no problem. Some force left. So that's a very simple system. If I tell you to derive its equation of motion, you will find, you may think this is easy, but you will find it's not that easy. It's very, very difficult. So I have this model. I will choose black pen. One, I is to M, AC is to FT. Then, of course, we have a zero junction. The force through this, and force on ground, and force applied here, all forces are same. You can just see from free body diagram, all forces are same. So force on ground, force in damper, force in the spring and damper combined, force acting on the bottom part of this mass. All are same. So it must be a zero junction. When you have mechanical series, it is zero junction. So you have this. What are in series? There is relative velocity from here, source of flow Vt. In series is this ground excitation. In series is this damper. In series is these two combined. These two combined. So this damper is in series, mechanical series. R is to R2 and these two. C is to K1, R is to R1. This is our model. I will make a copy of this model. I am not writing those M and other things. This is copy. This is original, that is copy of that. So of course everything is same. Now let us give causalities. So what do we start? We start with, oh, there was a FT is there. Okay. We start with anything, source of effort. Nothing happens. One junction, you have any one bond causal away, rest others should be near. We have only one near, we cannot tell. Nothing happens. No propagation. Source of flow, no propagation. Okay? So that is step one. AC and SF. Right? Could not propagate. No problem. Step two, not present. Then we will go to step three. this and this. So one by one we will go. Give anything you want, whatever you want. You can start with C, or you can start with I. So I go to step 3. So in step 3, let's give this I, this I. So this propagates. Fine, propagates. Just here. Let's see. This propagates, then this C could not propagate. Nothing happens. One junction missing is not there. So I propagated just one causality. I is to M get one extra bond causality by propagation. T is to K1. It did not propagate. So we didn't propagate. Something is left out. So what do we have to do? Now we have to go to step 4. So we have to go to step 4. East, touch, some bonds are get not causal. What does this step do? You have R, either this or R this. Give anything and propagate. So I do something with my color pen. This. So give whatever you want, some of one of the R. Let's say I give it here. So what happens? If I give it here, this becomes strong bond of zero junction, because one bond at zero junction can be near. So this comes here. Then this one junction, this must have one bond away. Two are already near. This must be here. That's what happens. Okay? Suppose I give this R here. What happens? Then this R bond, this zero junction has three weak bonds. All are away. Nothing is near. So this must be here. If this must be here, that is strong bond of one junction. One junction can have only one away. So this must be here. So same model, we could causal in two ways. Okay? Because we reached step 4. If we had not reached step 4, we cannot causal it in two ways. If causality is over by step 3, there is always unique causality. Whereas if you reach step 4, then there is non-unique causality possible. And if we could causal the whole model in step 4, then we have algebraic group. We are very lucky we don't have causal group. We have algebraic group. So what we got? Model got completely causal. In two possible ways. There can be many possible ways, some models, but in this case it was two ways only. Model has algebraic loop, fortunately no causal loop. That's it. Right. So causality assignment is not a big deal. Just tic-tac-toe, your causality will be done. And computers will do it before you know, in fraction of milliseconds maybe. So okay, So that's all for today. Tomorrow we are going to have this module-based test for a very two questions only. Two questions, 1 hour duration. Okay. And I don't know, I will fix the time. Maybe I will start it from 8:30 or 9. Okay. I cannot tell. Okay. So it will be 1 hour duration. Two questions are there. One, both the questions, one question is almost directly done in the class. Second question is done in the class, but in different parts. So basically, you can combine them to get the answer of the second question. Not at all difficult. You have to just draw the model. No causality assignment is not required. Just draw the models, write down the kinematic relations, and draw the model. Maybe electrical circuit is there, then you have to write down. You don't need to write down any relations. So every one of you must have got Moodle registration. I think everybody is registered because I have checked in Moodle. There are some 180 plus registered students. So we will have this test tomorrow evening.